Hey kids, welcome. Today we're going to talk about adding a little content to our calculus Bibles. Last time in class we went over limits. Specifically, we went over limits uh, with graphs, with tables. Today's our part 2 or our part B of that. We're going to talk about limits algebraically. Now, to do those, your first line of defense, your go-to guy here is direct substitution, meaning what I want to do when I'm given something like this, a limit as x approaches 5, x squared minus 3x plus 2 over 4x plus 7. First thing I want to do is I want to substitute. I want to plug in. So when I do, x squared is 5 squared minus 3 times x, 3 times 5, plus your 2. 4x plus 7 becomes 4 times 5 plus 7. Plug in, multiply, do what you do, order of operations. If you get an answer of 4 over 9, which 12 over 27 reduces to, yay, crowd goes wild, you're done. Thank an algebra teacher. Life is good in our world, you know. But sometimes weird happens, and this is an example of where weird happens. When I try to take a problem like this, x approaches 2, limit x squared minus 4 over x squared plus 3x minus 10. You say, okay, my go-to, it's plug-in time. Let's direct substitute. And I get 0 over 0 form. That's referred to as indeterminate form. I like to refer to as uh-oh form. It does not mean your answer is 0. It does not mean your answer is undefined. What it means is, really, I have no clue what my answer is at that point. That all it really means is that direct substitution crashed and burned. It may have an answer, it may not. I just know the methodology we chose to find it did not work. So we're going to try something else. We're going to try the factor and cancel method. Again, this works great if you can factor, number one, and if you get an indeterminate answer. So I'm going to keep my limit at 2, and I'm going to factor this difference of squares here, x squared minus 4, factors as x plus 2, x minus 2. The bottom, x squared plus 3x minus 10, factors as x plus 5 times quantity x minus 2. And you'll notice, coincidentally, the x minus 2's are going to cancel. Well, there was no coincidence to that at all. Matter of fact, I knew that x minus 2 was going to cancel. I mean, if you're lousy at factoring, the one thing I will promise you is that you are going to get an x minus 2 out of this. How do I know that? Here's why. Our direct substitution yielded that 0 over 0, that indeterminate form. If you recall from your pre-cal, when you get a 0 over 0 by plugging in, that results in a removable discontinuity. Maybe you heard the term whole before, and that's going to occur at x equals 2. So a whole at the x value of 2 means it has a factor of x minus 2. That is not a coincidence. It was not blind luck. It should have been expected. So, that aside, I'm not worried about what canceled, rather what's left. So I have my limit at 2. I'm left with x plus 2 over x plus 5. Now we go back to our go-to method. We direct substitute, we plug in, and I get an answer of 4 over 7. So a little inconvenience with the 0 over 0, the indeterminate form, but little factoring, little canceling, it's all good in our hood, you know. Well, what if factoring's not a particular strength of yours? What can we do? Well, option 2, I can try synthetic division. Again, I wouldn't do it first. I would first check to see how it goes with your direct substitution. We kind of knew this was going to happen because we've done this problem before. We're just going through a different methodology here. So I got the 0 over 0. I got the uh-oh. So synthetic division. Here's my division over here. Let's talk about where some of these numbers and whatever's came from. The first thing here is called our synthetic divisor, this 2. That came from right here. That's what your limit approaches. That's what I'm going to put in that box for my synthetic divisor. The 1, the 0, the negative 4, that came from the coefficients of our numerator. The 1 is the 1x squared I have from my quadratic term. The 0 is that I have no x's, no linear term, and the negative 4 was my coefficient on the top. So to do your synthetic division, bring down your leading coefficient of 1, multiply the 1 times the 2, which gives you 2, place that underneath your second coefficient. 0 plus 2 gives you 2. Again, a little multiplication by the synthetic divisor. 2 times 2 gives you 4. Negative 4 plus 4 gave you 0. You say, whoa, cool, 0. No, it's not a coincidence either. There's a 0 here. Synthetic division is also called synthetic substitution. So when I got a 0 on top by substituting the value of 2, it tells me I'm going to get a value of 2 when I synthetically divide as well. So don't get freaked out if that happens. It's okay. Get freaked out if it's not 0, okay? Next thing, I'm going to do the bottom. Again, synthetic divisor is 2. Coefficients are 1 for the x squared, 3 for the x, negative 10 for my coefficient, and bring down the 1, multiply, add, multiply, add, and again, there's my 0, which I knew was happening because of the indeterminate 0 over 0 form. Now, where you go from here is what's important. I know on top I started with an x squared, a quadratic equation. So when I synthetically divide, this 1 actually is no longer quadratic. It goes down 1 degree, 1 term, 1 power. So instead of being an x squared, it's just 1x and then a constant term of 2. Likewise here, I started with an x squared on the bottom. This 1 is not a squared, it's a 1x to the first power plus a 5. So this, after synthetic division, turns into 1x plus 2 over 1x plus 5. Same limit as x approaches 2. Do your direct substitution now, and 4 over 7. Okay, and say, whoa, that's the same answer as the last time. Yeah, it's the same problem as the last time. The method you choose to solve the problem is not going to change the answer. So the fact that you got the same answer doing it 2 different methods is probably a good thing. Option 3, L'Hopital's rule. I guess I should comment too on that last problem as well. If you're not particularly adept at synthetic division, long division would have worked too. You could have done long division divided by x minus 2 on top and bottom. Same answer. But L'Hopital's rule. It basically states if I have a limit as x approaches some value a of a function fx over a function gx, if that turns out to be that indeterminate form, that uh-oh form, or infinity over infinity, well, what it says is that the limit of f over g will yield the same answer as if I take f prime over g prime. Please do not confuse this with the quotient rule for derivatives. We are not taking f prime g minus fg prime over g squared. Not what we're doing here. These are limit properties, not derivative properties. All it's saying is if I get an f over g limit that's indeterminate, I can get the same answer if I derive the top or derive the bottom. So let's put that into play. Again, check first, direct substitution. Do not do L'Hopital's rule unless it is indeterminate form. If you do one with L'Hopital that is not indeterminate form, bad things await you. Incorrect answers await you. Don't ride that train, okay? So I know this one's indeterminate. We've done it a couple of times. So L'Hopital's rule says basically if I get indeterminate form, derive the top, and the derivative of x squared minus 4 using your power rule is 2x. Power rule on the bottom for derivatives, x squared plus 3x minus 10 derives down to 2x plus 3, and you plug in our direct substitution value of 2. Same 4 over 7ths we got doing it all the other methods. You know, find what works for you and roll with it. That's basically what I'm trying to say. So let's kind of sum up what we just talked about here. So if you're evaluating a limit as x approaches a of some function algebraically, again, your go-to guy, try and substitute. When you do, a couple things can happen here. First is you're going to get some value, 4 nines, 4 sevens, 12 over 15, negative 7 pi over 85, whatever you're going to get. If your limit gives you some numerical value, you're done. Just walk away. Well, what if you directly substitute and you get a 0 on top divided by some number k on the bottom? Well, I'm going to tell you first. It's okay for that to happen. 0 divided by any constant is 0. Well, what if the number you get, I say I get a number of like 5 on the top and a 0 on the bottom. Is that okay? No, that's KO. That's a knockout. That gives you an undefined or a non-existent limit, or a limit that does not exist. So, which brings us to our indeterminate forms. Our 0 over 0, our infinity over infinities. That's where your factor cancel, synthetic long division, or L'Hopital's rule comes into play. Last thing I guess I want to talk to you about is, this ties into your limits algebraically, are limit properties or limit laws, I guess is what I have them called here. It basically states this. If I have a limit as x approaches a of a function f plus a function g of x, basically you just take the limit of the first, limit of f, and add it to the limit g, or the limit of the second. Same thing's true here with difference. Limit of as x approaches a f minus g of x, limit f minus limit g. Product for multiplication, here's the suspense, drum roll, limit f times g is limit f times limit g. Quotient, same drill. Limit f over g of x, limit f over limit g. This one looks a little weird here. I have a limit as x approaches a, k times fx. You say, well, what's the k? Well, k is some constant, some coefficient. I've heard it called a scalar also. Basically what it means is when I have a limit as x approaches a of some constant times a function, you do not take the limit of the constant, you take the limit of the function, and whatever that yields, you multiply by the constant. We're going to do some examples to show you how that works. And the one that tends to confuse a little bit sometimes people is limit as x approaches a f of g of x. Yeah, that's your composite function, your function within a function. It doesn't work quite like these other guys, you know, where you take the limit of the first and then the limit of the second. You don't take the limit of both. It's not limit of f, limit of g. What it is much like you worked with your pre-cal and your algebra 2, you work inside out. So you take the limit of the inner function, gx. That's going to give you some value. You do not take that and use the limit of the outer function, f. Rather, you take the limit of the inside, which gives you some value, and then you take f of that value. Not the limit, but rather the functional value. So, here's an example, or a couple of them. I have two graphs here, one for an fx, another for a gx. And in example A here for number 1, I have a limit x approaches negative 3 of f plus g of x. So, again, my property tells me I go limit at negative 3 of f plus limit negative 3 of g. So at negative 3 for my fx here, I see a left-handed limit approaching approaching 1, a right-handed limit also approaching 1, left side meets right side. So my limit for f is 1. And at negative 3 for g, I see a dot here. Just walk elsewhere. I'm not interested in the solid dot. I'm interested in the left-handed, the right-handed limit, which seem to converge here at negative 2. So I get limit at negative 3 of f was 1. Limit at negative 3 of g was negative 2. 1 plus negative 2, negative 1. Product. If I have a limit x approaches negative 4 f times g of x, Again, break it two ways, or into two different limits. I have a limit at -4 of f, a limit at -4 of g. At -4 here for f, I see a left limit, a right limit, both converging at 2. So I'm going to replace limit f at 2. And at -4 here, I have a left limit and a right limit converging at -1. So 2 times -1, -2. Okay, our constant multiplier, our scalar, if you will, limit x approaches 4, 7 times fx. Again, do not take the limit of the 7, take the limit as x approaches 4 of fx. So at 4, I see a left and a right-handed limit here, appearing to meet at the y value of 3. So my limit at 4 of fx is 3 times the constant 7, 21. It's pretty straightforward stuff. Which brings us to the composite function one. Again, same graphs of f and g, I believe, maybe a little different, I don't recall, but that's not important. I have a limit as x approaches -3 of f of g of x. Again, according to our limit property, that means I'm going to take f of, or I'm going to evaluate the function f at the inner limit. So at -3 for g, again, here's the dot, just keep walking. I want left limit, right limit. So my limit at -3 of g gives me -2. Again, I'm not looking here and say, oh look, the right limit at -2 for f is 4, the left limit 0, they don't meet, so it does not exist. No, I am looking for the value of the function. I'm looking for a solid dot. It's right there. I do not take the limit of the outer function, only the inner function. So that's 0. Last problem. You'll notice it looks eerily similar to problem A. Limit x approaches -3. It's a composite, only instead of f of g, I did g of f. The reason I did that is twofold. One is I want to see if order matters, so I want to determine if, basically, if limit composition is commutative. You know, like addition is commutative. 5 plus 2, 2 plus 5, same deal. Multiplication is commutative. 8 times 3, 3 times 8. Subtraction, division, not so much commutative. I want to see if this actually is. And second of all, I just want more practice to evaluate them. So again, to evaluate this, limit of inner, evaluate function with the outer. So I'm going to take the limit at -3 of my inner function, f, and here we are at -3. Left limit, right limit seem to converge here at 1. So I'm taking g of 1. If I go to 1 here for g of x, I'm looking for a solid dot. See, I'm not saying, okay, there's a left limit or right. No, I'm looking for a dot at 1. And I see a hole. I see a hole. I see a whole lot of nothing as to what I'm looking for here. So I get a limit that does not exist. So I know that limit composition is not commutative. Order does matter. So I hope this helps. Thank you.